Okay, so this video is about arcs and chords of circles. So first of all, know that this is a circle. This is a circle, and the name of the circle is circle P. This is a symbol for circle. There's a little circle with a dot on it, and the letter that follows it tells you what the center is. So that means my center is at P. So I see a P here, and that means it's the center. It means no doubt about it, that is the center of that circle. Even though it didn't really look like it, I tried to make it the center. Anyway, it means that's the center of the circle. So if I have more points in there, I know that P would be the point that's the center, and other points are just points that's inside the circle. All right, so that's the first thing you need to know is about it. That's how you name a circle. With a circle and a dot in the middle and the letter that follows it, names the center. Next thing is this. I drew a radius here and a radius there. This angle here is called a central angle. Why is it called central angle? It's an angle at the center. All right, so as the angle's vertex is at the center of the circle. So if my angle's vertex actually lies right there on the center, which is P, we call that a central angle. I usually use a curve, whatever represents the angle. Anyway, so that's a central angle. All right, another thing to know about that angle is this angle has an arc. It intercepts. This is the arc. You need some letters. The name of this arc, let's say this is A, this is B, and now this is arc AB. All right, what I mean by arc AB? It means it starts at A and goes to B. So that's arc AB. Now, you could have said, well, it starts at A, and you could have went the other way, around to B this way. And you'd be looking at a whole different arc. So because of that, we got two kinds of arcs. We got major arcs and minor arcs. To be a major arc, it has to be greater than 180 degrees. All right. Or to be a minor arc, it has to be less than 180 degrees. And if it's actually equal to 180 degrees, semicircle. Equals to 180 degrees. And it would look like a half circle, where the center would be somewhere there, and that would be the semicircle. It would be half of it. So it's each one of them. You got major arcs, minor arcs, and semicircles. Now, in order to be a major arc, typically the name of a major arc, you need 3 letters. So I would need to give it another letter over here. Let's say G. If I want to name this arc, the one in the back here, now I have 3 letters, so I can name it. And this would be named arc A, G, B, or arc B, G, A. Depends how you actually want to name it. And it also has a central angle that's here. All right, so you already know that on a circle you got 360 degrees. So if it's 360, take away the 70 you're already given there. These are 290 degrees. This is a 290 degree angle. All right, so that means that the measure of arc AGB is 290 degrees. All right, so 280 degrees. Anyway, so that's how you name an arc. 2 letters for a minor arc. That's 2 letters. And you need 3 letters for a major arc. All right, you don't have to put it where I put it behind, but just know that's what it is. 3 letters for a major arc. Okay, so that's pretty much all you need to know about central angles. Again, central angles are equal to the measure of the arcs. But the other kind of angles in the circle as well. Let's talk about those now. All right, so in this circle, we got a circle J. So the center is at J. And I could have an angle whose vertex is on the circle. This has a different name. It's not a central angle because vertex isn't on the center. It's actually on the circle. The name for this is inscribed. And one thing you want to know about inscribed angles is vertex is on the circle. Another thing you want to know is this. The measure of an inscribed angle is equal to half the measure of its arc. It's kind of nice to know if you're trying to figure out angles of a circle. So what we know is whatever this arc is, this angle here is called angle 1. is equal to half of it. So whereas the central angle is equal to the same thing, whatever this arc, let's say this arc is 80 degrees. Well, the central angle is 80 degrees, because it's right there on the center. But the angle that comes all the way back to the circle here, the central angle, isn't that, it's half of 80. So let's say the measure of angle 1 has equal to 40 degrees. Really nice to know when you're looking at circles in geometry, to know that that inscribed angle is half of its arc. All right, hold on. All right, so for example, using this picture, what is the measure of arc MLK? All right, so arc MLK, it's going to be this arc starting at M, going through L, ending at K, and then it actually figure out the measure of that. So what I see is this is a right angle, so it's 90 degrees. And I see this arc has two sides, this angle has two sides that form arc MLK. So since that's an inscribed angle, right, because the vertex is on the circle, whatever this is half of the major arc here, or the arc, whatever it is here. So if that's 90, well, this has to be 180 degrees. So it basically has to be a semicircle right here. So measure of arc MLK has equal to 180 degrees, because it's got to be twice that angle. But a really nice thing to know by knowing that little theorem there about arcs and inscribed angles. All right, let's go further. All right, this is circle K. Now what we all know is if I made a segment that went through the center, K, right? You know a name for that. Let's say this segment is AB, and we say the segment AB is a diameter. Been learning about diameters for quite some time now, probably goes back several years, and everyone knows that's the diameter of a circle. However, suppose I gave you this segment. Let's put it right here. And let's name it FN. All right, segment FN. We know for certain it's not diameter because it doesn't go through the center of the circle. It's too short to be diameter because it can't go through the center of the circle and still be on the circle. So because of that, we have another name for it. FN is a chord. And we spell it a little bit differently how you think you spell chord. All right, so now this is a chord of a circle. Any segment that has endpoints on the circle is said to be a chord of the circle. So technically diameter is a chord as well. It's just the longest chord of the circle. So any segment, no matter which direction it goes, we call that a chord to a circle. So that's by definition of a chord. So again, a chord is any segment that has endpoints on the circle, and by definition, a diameter is the longest chord you can possibly have inside of a circle. All right, nice things to know going further. All right, so this is a new circle called a circle O. And this is chord PJ, this is chord SQ. If you remember from geometry, this little hash here means those two segments are equal to each other. So we got a theorem in geometry that says if two chords of a circle are congruent, or two chords of congruent circles are congruent, then this arc that is intercept is equal to this arc that's intercepted. I give it two hashes. So if those two segments were congruent, it would force the intercepted arcs to be congruent. That's a theorem. So the theorem is if two chords of a circle or congruent circles are congruent, then intercepted arcs are congruent. I hope you guys are okay with me using these symbols. This is geometry and we use lots of symbols. Just so you know, this symbol means congruent, if you didn't already know. Congruent essentially means the exact same size. So it just means exact same size, exact same shape. We could say equal. Equal means the same, and they're not necessarily the same figure, it is the exact same size. And this circle means circle. Whenever you see that symbol with the dot, a circle with a dot in it, it means circle. All right, moving on. Okay, let's say we have circle N. Let's give circle N a chord. Let's name that chord OP. Let's give it a second chord. Let's name this chord TY. All right, now, what's special about the second chord TY? We might say, well, it's a diameter. Great. If you notice that chord's diameter, what's unique about it is, if you have a diameter and it intercepts another chord of the circle, such that it's perpendicular to it, like it meets at a right angle, automatically that diameter not only meets at a right angle, but it bisects it. All right? So let's put a point here. Let's call this point J. And so basically the theorem says this. If a diameter is, the symbol is perpendicular, if a diameter is perpendicular to a chord of the circle, then a diameter bisects the chord and its arc. So not only does it split this chord in half, two equal parts, it splits its arc into two equal parts. So this part is equal to that part. Whatever it was is now split in half. All right, so it's a nice little theorem to note. I'll get that down. It's a nice little thing to know when you're trying to prove something or you're trying to get to the next step in solving a problem. All right, a neat theorem. All right, let's say we got this new circle. This new circle is called circle A. And let's give it two chords. Now it has a chord BC and it has a chord LM. All right, now suppose those two chords were the same distance from the center. Let's say this distance, a straight line there, and it's perpendicular to it. That would be the shortest distance from it, a perpendicular line to it. And let's say this value was X, and this value here is perpendicular to it, and it was also X. But since both of those X's have to be the same, these two chords are the same distance from the center. Because the theorem says, if these two chords are the same distance from the center, then these two chords have to be congruent and the arcs have to be congruent. So that's the theorem. The theorem says if two chords are equidistant meaning equal in distance, equidistant from the center of the same circle or congruent circles, then the two chords are congruent. And conversely, if they're congruent, the arcs have to be congruent as well. All right, so another nice theorem to have. I will copy that down as a note. I got one last example. All right, so this section doesn't really deal with circles. We are going to work on the coordinate plane, and it's very important for you guys to understand two formulas to deal with coordinate planes, and that's distance and midpoint. So this is the first question. Find the distance between points M and T if M is at 1, 2, and T is at 5, 4. So point M must be here. T must be here. All right, so you want to find the distance from there. That'd be a point connecting those points directly. Now, one way we could find it is we can use a Pythagorean theorem. You simply figure out the distance along the x-axis here and the distance along the x-axis there. When it's a slanted distance, it's a bit harder to find, but if it's a horizontal distance or if it's a vertical distance, we can simply count off the space in between those numbers. Or we can start on the right side and subtract backwards. So we either count 1, 2, 3, 4. Or we can start on the right side, 5. Subtract backwards, subtract the positive 1. So it's 5 subtract 1, which is 4. So the length here is 4. And here, I could start at the top and subtract down. So it's 4 subtract 1. That's 3. So this length is 3. So those are two sides of the right triangle. One side is 3, one side is 4. So basically what you could do is, well, a squared plus b squared equals c squared. And you can figure out what c squared is. This formula was derived on that fact, that a squared plus b squared equals c squared. So basically what I decided was, if I solved a squared plus b squared plus c squared, I'll get the square root of a squared plus b squared equals c. Now, a is the distance between these 2 points. So if I start this x value, 5, subtract the other x value, 1, I'll get the length 4. Hence, this is why the formula says x of 1 subtract x of 2. So the formula, if you actually use the coordinates, you would name them x1, y1, x2, y2, and you plug all those names right in. So you'll take 5 subtract 1, and that'll be the square root of 5 subtract 1 squared plus 4 subtract 2. So 4 subtract 2 squared, and you'll wind up having the correct answer. So the square root of 4 squared plus 2 squared, square root of 16 and 2, that's 20. Square root of 20. I think we got some bad math here. Apparently that was 5, 4. It should have been. And this is 1, 2. So that distance there shouldn't have been 2. That distance there should have been 3. I'm sorry, it should have been 3. It should have been 2 if I extracted properly. And that's one of the reasons why you want to have more than one way of answering the question so you can verify your answer. So anyway, it should be square root of 20, which is a decimal, so I'm going to leave it there. But anyway, that's all I have. Good luck.